I'm very pleased to be here and see so many people interested in FL and open source in general. I think the combination of these two topics are very important for the future of AI. So that's great to see everyone here and even online. So this talk will be maybe slightly less technical than the previous ones. And my goal here will be to convince you that doing self-supervised learning with federated learning makes sense, that there are a lot of opportunities there, and also a lot of challenges that we have to overcome. And for now, well, that's not the case. So the very first thing that we have to understand is, what is self-supervised learning? So the thing is, it's already impacting your daily lives if you are used to use technological products. Large language models, a big part of them are using self-supervised learning. So ChatGPT, BARD, GPT-4, 3, all of them. And in other modalities as well, you can think of speech, for instance, if you have heard of Wave2Vec, XLSR, Data2Vec, all of them, they are trained on with self-supervised learning. And they are already powering a lot of products that are deployed around us. And there is an example here on the slide, bottom left, where we have this hate speech issues for Facebook that has declined over time. And it has been said that it was also helped with SSL. Scientifically speaking, well, it's also a very, very, very active research direction. Here you have the evolution of the number of occurrences of self-supervised concept in titles of papers published at the Interspeech Conference. That is basically one of the largest international conference for speech-related things. And you can see that basically out of 1,000 papers, 140, so like 14% of them will contain something related to SSL in the title. So much like graph neural network or GANs or CNN when they were invented, you can see that there is a lot of interest very quickly in this topic simply because it is working and it's beating everything that we used to know. Another good sign of this is the number of downloads that we can check from just Hugging Face, basically. So those numbers are monthly download, and we can see that some of them are above 100 million monthly downloads, for instance. And for speech models, like 62K, I mean, that's a lot of downloads of the model, right? So it's a bit unclear, oh, Hugging Face is computing this, but still, right, it's massive. There is a huge interest for SSL models. So now that we have seen how impactful it could be just right now, we have to understand better where it comes from, what it means. And so we have to go down to unsupervised learning to understand self-supervised learning. So if we want to define unsupervised learning, it's very simple. It's just a type of algorithm that learns patterns from unlabeled data. Great. A good example of this is an autoencoder, okay? The thing is, if you ask me to define self-supervised learning, I will tell you this is a type of algorithm that learns patterns from unlabeled data. And a good example of it is an autoencoder as well. That's my definition. And if you go around Twitter or people that are actively pushing for SSL, they might say, wait, this is not really true. With SSL, the labels come from the input signal. I mean, that's also true for an autoencoder. Okay. The thing is, we can still try to slightly redefine SSL. And we could say that for SSL, instead of just like unsupervised learning, we could say that the labels that we are using, they are extracted from the input signal indeed, but they have been very carefully designed to serve a certain purpose. So if I know what will be my downstream task, large language model, for instance, we know what we want to do with them, or for speech, we want maybe to do speech recognition, then maybe I can design the way I extract automatically the labels from the input signal so that it corresponds to what I want to do after. That's maybe the best definition of SSL we can come up with. Now, how is it working? It's fairly simple. We have to understand this, why it is very important to use FL plus SSL. So very briefly here, what we want to do is say we have a very large pre-training data set. In this case, it's speech. we extract some common features out of it. Okay, so this is the spectrum that we see here, and we put these features into a deep neural network that we call an encoder. This encoder usually is a transformer. It's true across most of modalities as well. And the output of this encoder will be a new set of features, right? So it's like our pre-training data set transformed into a new set of latent features. And this set of latent features is what we really care about, because they are basically enriched features with context from it. And this is what helped the model to perform so well. All of this is trained, it's simple. So we still have this encoder, we create this new set of features, and then we just compute some SSL objectives, loss functions out of it. Many of them exist, right? So you can have a simple reconstruction of the signal, for instance, and a encoder, or a fancy one, but it's still an encoder. And you can also have other losses like, I don't know, contrastive loss, or even a bunch of non-contrastive objectives as well. But this is not really important here. This is how you train it, right? So you go with this super large pre-training data set, and once you're done with the training, then you just freeze, or not, but you just get the encoder parameters, and you use it for your downstream task, right? So the downstream task can be for speech, for instance, emotion recognition, speaker verification, speech recognition, text-to-speech, whatever, right? And so you get this encoder, you have your downstream data set that is quite often much smaller, of course, than the pre-training data set. You still extract your features, and then you go through your pre-trained encoder, and you obtain this new set of features that are enhanced compared to the standard acoustic features. And then this new set of acoustic features, or features in general, if it's not in the speech domain, then you put it into the downstream model. That can be anything, right? CNN, LSTM, transformer, whatever your task needs. And then you do your downstream training. And that's it, right? That's the whole, how to say, process of applying SSL to a downstream task of interest. For the objective function, as I said, the only point that is important to understand is that most of them are shared across the domains, speech, image, text. They come from the same ideas. It's just that they have very slightly different implementations because of the domain. And again, that's the point with SSL. We want to design slightly the loss so that it adapts to what we want to achieve in the end. Right, so how does this thing perform? So on the left, you have the leaderboard of ImageNet, one of the best, biggest, largest benchmark for image classification. Maybe not the best one, but it's one of the most known. Well, if you look at the top 10, or even top 6 in this case, I think, all of them are using something related to SSL and other external data. On the right side, which is for speech, that's a big table. So let's focus only on the blue frames. So you can see the first frame here, that is F-bank. So that's just standard acoustic features, no SSL. And we will go through ASR, that is here, which means speech recognition. So here the number lower is better, okay, because it's the word error rate. So we want the number of errors in our transcription to be the smallest possible. You can see that we have 23. And if we use the largest SSL models available right now, we go down to 3%. So we go from 23% of errors to 3%. The gap is massive. And this is why everyone is jumping into this, simply because if you have a large data set, a lot of compute, then nothing can keep up with SSL in your downstream task. Nothing. As of now, nothing. Problem. It's very hard to train them. Very, very hard. We won't even talk about like LLMs and things like this is another level. But let's say even for speech, right? Even for speech, you might need 100 GPUs for a week or month of training to do this pre-training. It's not even the downstream task, right? Like just the pre-training. So like the actual impact in terms of energy consumption, carbon emissions, all this stuff is quite huge. And the thing is like, well, you have one model that you can reuse multiple times. The thing is, we keep retraining them because we want better ones, right? So that's not really true as well. Other problem with this, not a lot of people can use 100 GPUs or 1,000 GPUs to train their model. So if you look to the speech modality, those 14% of papers at Interspeech, all of them rely on 2 companies, Facebook, Microsoft. 14% of our submission last year at Interspeech depend on those 2 companies. I won't comment on this, but we should think about it. Right. Also, there's another problem. We won't go into the detail of this one, but it's simple, right? Like SSL is not magical. So if you have 1,000K hours of speech, if you have clean speech with one speaker and you want to do something that is super noisy, a lot of reverberation, a lot of speakers, it will just not work. So we just make the assumption that since we have a bigger data set, then we will have a better representation of the world that we want to deal with. It's not always true, right? And in speech, for instance, it's not true. And we have a large shift in performance that is expressed in this table, but we'll skip it. Basically, it's just not magical. If you had biased with supervised model, you still have them with SSL. They do not disappear. So OS disconnected to SSL, to FL, sorry. Well, here to understand this, we have to check what FL can offer and what SSL benefits from. The very first point is that FL, very theoretically speaking, can offer infinite data, right? If we consider cross-device FL, we have 1 million devices around us. We keep taking pictures of I don't know, birds or plants or whatever on the wild. Well, we keep having data. We have an infinite amount of data potentially to train our model. SSL likes this. It likes very much because we need a lot of data to train this. And if we want also to remove these biases and think, we need a lot, like have a lot of data coming from a lot of different devices as well. Second point is like with FL, well, it's also mostly unlabeled data. Well, it's not only true for FL, it's true in general. We have much more unlabeled data than labeled one. But with FL, it's even stronger, right? Like if you talk to your Google Assistant, you won't say, okay, here, this is not what I said. The correct question was, or the correct answer was, right? You just talk to it. You don't label the picture that you're taking on a daily basis. Great. We don't need labels with SSL. This is exactly what we want. This is exactly the kind of data that we want with SSL. Privacy, we don't know, right? Because, I mean, we often say that FL equal privacy. Well, we had a lot of talks today to showing that if you want to achieve privacy things with FL, you need privacy adapted methods to do it, right? Like it's not magical as well. SSL is not introducing new guarantees on privacy. I guess it's even worse because you are just using even more data. So here it's a bit of a like blurry line. We don't really know. And finally, of course, I said we need a lot of compute. If you think of FL, right? Even cross, whatever, like if it's cross-device or cross-silo, cross-device, you have 1 million smartphones. Well, that's a lot of compute, right? If you think of it, I guess in one round, that's a lot of compute. Even cross-silo, if you have 10 institutions that have small servers, maybe a single server of this institution couldn't achieve SSL, but if you combine all of them, then you can do it. So basically combining SSL and FL, it's natural. It feels natural. The nature of FL is like a lot of heterogeneous unlabeled data with a lot of compute. This is the definition of what we want for SSL. So to understand properly what FL plus SSL means, we'll see the two different definitions that we can come up with. So we have upstream federated SSL and downstream federated SSL. So upstream federated SSL means what we are achieving with federated learning is the actual SSL pre-training. So on the local device, we do the SSL pre-training that we've seen, the top row of the first graph we've seen. So we have our big model on device, and we want to train this GPT model, FedLM, on device. So that's the upstream federated SSL. The downstream federated SSL, on the other hand, is where we want to achieve the downstream task with the SSL model already trained, right? So we have only the labels on device. So we do supervised fine-tuning on device, and it's not the SSL pre-training. The SSL model is already pre-trained. So here we wish to learn a task-specific model, a speech recognizer, an image classifier, whatever. These are the two models. Now, quick example of them in practice. So if we want to do cross-device FL, so again, we want to learn the SSL model. Let's say we have a huge fleet of different devices, smartphone, TVs, tablets, fridge, whatever. We have a lot of things, right? So here we can train on all of them our SSL models with all the different modalities because we don't have labels. right? It's most likely that when you will be communicating with your speech, whatever smartness is inside, you won't be giving him any correctional labels. This is great because for speech, for instance, right, you will end up with a lot of different noises, a lot of different speakers, and a lot of different microphones, right? We will have a very large heterogeneous data set. This is exactly what we want with SSL. And so by doing this, we will end up with a very robust and high performance foundation model for speech that we can then apply for whatever that we want later on. It might be something that is not linked to federated learning at all, but at least the SSL model will be learned in that way. If we want to do downstream now, well, we can also, in this example, we combine both upstream and downstream with a very specific example where we can think of health facilities that have both kind of data, right? So they have labeled images that have been annotated with respect to some diagnosis. And we also have a labeled one because they have not been used for this diagnosis or they are not relevant, but still we have them. So how can we leverage the entirety of the data set and not only one part of the other? So the idea here is very simple. You start by doing upstream SSL, federated SSL. So this means that on each institution that you have, each health facility, you will do this SSL, federated SSL pre-training on the unlabeled data, right? So just like we've seen in the previous slide. And once this is done, once you have your SSL model, then you go into a second mode where you will send to each institution this foundational model, and they will start doing the fine-tuning on the target, on the labeled set of images they have, right? So by doing this, at the end of it, you will end up with something that will help you with medical diagnosis, for instance, that have been trained on the entire set of images, labeled and unlabeled, right? So this is leveraging the two upstream and downstream SSL case. Now, this was a paper, by the way. Impossible to read. Great. Now there are a few problems, few challenges, I have to say. Because all I've said about large data sets, heterogeneity, all these kind of things that look super cool for SSL, in fact, it's also a big problem. So we know that with FL, we end up with non-IID data most of the time. SSL models, a lot of them are quite unstable when you train them. And this is why it's almost impossible to train them, to pre-train them from scratch with federated learning. I think that one of the paper that won an award today was doing this federated SSL for audio, and they start from something that is already pre-trained, right? Because otherwise it doesn't work. It's very hard to make it work. So this is the first challenge that we have to address. We have a lot of data, but for some reason, when we start training our SSL model on them, it doesn't work. It doesn't converge. Then there is an actual batch of challenges because they are all connected. So alongside with this non-IID-ness in the data that you have with FL, you also have the problem of the amount of data that you may have in each device, right? So you might, for speech, you might have one smartphone that has 10 seconds of speech, while someone that has maybe 2 hours, right? And the problem is that those SSL models, quite often they require large batches. So if you want to just do one update of training, you need maybe, I don't know, 1 hour of speech, for instance. So this is a problem. Compute capability wise, same problem, right? I said you have 1 million devices, so you can train on them. But the problem is you need a certain amount of compute in each of those devices as well, right? Because the models that we're talking about have maybe 1 billion parameters, 100 billion parameters, or a few hundred million parameters. Training this huge transformer on your small smartphone without degrading the user experience through the day, it's not simple, right? It's not trivial to do this. And also there is only little storage, right? If we just take an example here, this is a small one, like it's a speech SSL model, multilingual one. You have 2 billion parameters in it. Each mini step requires 3 hours of speech. So this means that if we want to train locally this SSL model on each device, we need 3 hours of speech. It's most likely not going to happen anytime soon. Other problem right? The model size is 9 GB. You don't want to put a 9 GB model size, like if you want to train it, or you uncompress it before training it, and then you, but that's like, it's huge, right? Like it's a big model to manipulate. And if you go with a large language model that has hundreds of billions of parameters, it's another issue. So of course we could say, we could simulate a large batch size with many clients. Great. What about the communication? What about the communication cost? If we do this, then we have like crazy number of communications. And we know that communication equal energy, equal as well slow training times. So how do we solve this? We could use smaller models, but if you use smaller models, then SSL is bad, right? Because we've seen that if you want good performance, you need big models, and then you can compress them. But if you want to train them from scratch, you need a lot of parameters. Another issue is that with FL, we have indeed an unlimited amount of data. But the problem here is that this data is coming in with like as a continuous flow. As I said, people keep taking pictures. So you can say, okay, in the production scenario, that's fine. I will just keep rolling my model every month, update it. But some people might just say, why not updating it on the fly while the data are, I'm taking a picture this morning of something, then during the night, my model is training and sending to the server. So this is linked to continual learning, and that's a very blurry line because we don't know, right? Like there are very, very few papers about this. The last biggest problem, in my opinion, is the evaluation. We know that evaluating FL, just FL, evaluating FL methods, algorithm properly to understand what will be the impact on the real world is already very hard. We know that all the data set that we are using for FL, only a very few of them are actually representing something that is plausible in real life, right? Just think of non-IIDness or the amount of data we have or the nature of the data we have, right? For SSL, you need a super large data set, right? We don't have much SSL data set available right now. For speech, most of the models, they rely on the same ones, right? Like we have 4 of them, we combine them together, that's 100K hours of speech, and everyone is using this. So if you combine the difficulties, so all the requirement of evaluating with FL, plus all the requirement of evaluating with SSL, you combine them together because you are doing the 2 at the same time. It means that you need a super large data set that can be partitioned, that is non-IID, and that can be used easily with FL. Well, it's not straightforward. Like there is no answer to this right now. So you don't know what will be the impact on the real world yet. It's just like, okay, good to compare our methods, but we have no idea what will happen when we will put this in production. So there is no ultimate solution, right? As I said, research is extremely active. And I think most of the papers, every time they focus on one problem at a time, right? Which is great. You can solve all of them at the same time. But then the other issue is that then you don't know if you combine everything together, if it will still works, if you want to try solving all the challenges, how to do it. So yeah, there is like still a very long way to go to innovate with this. And basically, the best thing I can say here is try it because it's a very new field. I will say like the combination of FL plus SSL is a very new field of research. So there is space to get accepted, less competition, right, in conferences. So that's great. And as I said, also, it's very natural to combine them. I think that there is a huge potential in terms of impact here in the outside world. So if you want to do this in the speech domain, of course, you can use, it's not SSL on the right, it's FL, but anyway, you can use Flower to achieve federated learning, and you can use the SpeechBrain toolkit to the whole SSL plus downstream speech recognition, speaker verification, emotional recognition, whatever. There are already, I think, a few tutorials, at least one that I'm aware of combining Flower plus SpeechBrain. So it's not for doing SSL, but I'm pretty sure that the paper of this morning has the code available somewhere, certainly. So it's already FL plus SSL. So everything is open source. You can just already jump on it and hopefully be the next publication on this topic. Right. So I saved a bit of time for the questions. So hopefully, I don't know if I'm too late or not, but That's it.
Thank you.
Thanks, Titouan. Great talk and great insights, as always. So there is obviously a discrepancy between the size of the models that we want to train and the capabilities of devices that we have out there right now deployed. Do you see this being breached only by means of architectural changes or algorithmic changes, or also on the hardware side or the system deployment side, you see something happening in between? Thanks.
Right. So there is one paper from someone here in the room trying to see when we will be able to do SSL with FL on device at the current increase in terms of compute capabilities. It's quite far away, but the problem also, as you mentioned, is the size, because as we will get into the future, the model size will also increase. So to me, for sure. So the thing is, like, I only know in speech. I'm not, text and image is not really my domain, but basically in speech, models are very inefficient in the way they train. Like, using such super large batch size makes in the end no sense. And there have been a lot of research pushing this down to now we can have maybe a few minutes instead of hours. It's not pushed at the same scale in terms of downstream performance still. But I think there is a lot of improvement to do in terms of going into the other direction of what the big names are doing. They are just scaling. Like, that's super hard to do, right? Like, I'm not trying to downscale what they are achieving. It's super hard to do. But the thing is, it's not like a specific line of research. We can do the opposite and say, let's try to fix this level of performance and achieve it with like 10 times less compute power, for instance. This has been done in speech, for instance, with data to vec that is 10 times more efficient than wave to vec. So if we keep doing this, and since the hardware keep increasing in capacity, I hope it will catch up at some point, hopefully. Otherwise, one big question to me is, like, I said, like, if you reduce the model size, then you end up with something that doesn't work well with SSL. Why is that? Like, to me, this is not clear. Why you absolutely need this huge amount of data, huge amount of neural parameters when you train it, and then you can compress it and still it performs well. But if you start with the standard small size for the pre-training, then it doesn't work. So here there is another line of research where we can say, why not try to find this super well performing model from the beginning? But what is well, that's one of the good aspects of training super large model is something that only 2 companies can do, because all the rest of the people focus on trying to lowering down this barrier, right? So I don't know if this answered, but this is what I can say.
Other questions? I think, yeah. Okay, we have one in the front. You go.
Hey, I noticed that there was one part that was just a question mark on the slide, which was SSL and privacy. I'm wondering what the state-of-the-art approaches are towards being able to do self-service. I mean, like, it's learning its own, it's like learning from the data, so there's only so much you can do, but are there ways to make it so you can sort of guarantee privacy, but also pick up sort of signal from the data?
Right. So there is another paper. I think it's coming actually from the same lab than the one that did this paper with Tuvek SSL training this morning, or it was this evening. But basically, they showed that by pre-training in a distributed manner, so it's not really FL, but it's very close to it, an SSL model, you were able to retrieve, or at least classify properly, the identity of the speakers just from the data that were transmitted. So again, I mean, this is like, you can really think of the SSL model as something that will just create a new set of features enhanced, so they actually contain, right? The model is trained to still contain the signal, the original signal, right? So it's not trying to introduce any noise or anything. So if from the original features that you had, you can actually retrieve information, which is true, right? Like for speech, it can tell you the age, roughly the age, I mean, many information that you don't want to disclose. Then there is no reason it should be even worse actually from the new features extracted from the SSL model. So to me, it's even worse, I think. But the good thing is like it will be blended in a huge pool of people, so hopefully slightly harder to discriminate, but maybe even not. I don't know because there is no work on that.
Thank you. Very, very interesting topic. I'm curious about kind of some of the issues of fairness and data set bias and so forth that tend to come out when we do SSL. And what do you think are good approaches to combat this in a federated setting?
Okay. So in the centralized fashion, the answer for the speech domain from the major actors doing these models that have been shown to be biased is use more training data that are counteracting toward this bias, right? Because I guess it's the cheaper answer to come with. You just need more data. Okay, great. For FL, that's a good question. For FL, I honestly don't really know. So the good thing with FL is that the biases that we will end up with might not be related to, for speech, for instance, the acoustic nature, because you can consider much more devices. So you will have something that will be robust to noises, perturbations in the microphone setups and things like that. But if we think in terms of human biases, then I think there is, for now, nothing special about FL. And maybe that, but then there is a problem with privacy at this point. If you have metadata information about your clients, gender, things like that, maybe you can try and play with this when you select them. But I mean, those are roughly the same tools that what we have for centralized. So yeah, I'm not sure that there is anything special here. We will have the same problem, so we have to deal with them. But
cool. Well, I think that's all the time we have for questions. Thank you for the fascinating talk.